Swayam Prabha. Digital India. Educated India.
In some of the earlier stability problems that we had encountered in this course, such as the Rayleigh plateau instability or the stability of a thin film, we had made important simplifications to focus on the essential physics of the problem. For example, in the Rayleigh plateau instability, we had ignored the viscosity of the filament. And in the stability of the thin film, we had assumed that the horizontal extent of the thin film is much larger than the vertical extent of the thin film. We call this the lubrication approximation. By using these important approximations, we had basically we were able to simplify the equations and then carry out a stability analysis on the simplified equations. Now, one thing that is also common to both these problems, that is the Rayleigh plateau instability and the stability of a thin film, is that we had ignored the variation of surface tension at the interface. Now, as we know, surface tension can vary at an interface because of a number of factors. You could have temperature variations in the fluid, which could lead to surface tension variations. We could have surfactants present in the liquids, and that could lead to surface tension variations. And we could also have a liquid comprising of our solution may be comprising of two liquids with different values of surface tension and different volatility. And when you have evaporation of one liquid relative to the other, then again you can have surface tension differences at the interface. All these surface tension differences result in a motion at the interface because of what is called as the Marangoni stress, and this motion causes a motion in the bulk as well. Now, what we want to do in this lecture is to set up the foundation for the so-called Benard-Marangoni convection or Benard-Marangoni instability. Now, this problem goes back to the early works of Benard, where he was studying he was carrying out experiments by heating a fluid from the bottom and observing what convection patterns are set up. Now, in the initial days, it was thought that this instability that Benard observed was a buoyancy driven convection, and Lord Rayleigh developed a detailed theory for this, taking density differences into account when you heat a fluid. But much later it was realized that the original convection patterns that Benard observed may not be because of buoyancy effects at all, but maybe because of surface tension variations. We will also see under which conditions we can ignore buoyancy effects when we do the analysis. So we want to understand the work of, we want to develop the theoretical model for this kind of convection. This was first theoretically studied by Pearson in 1958, and we'll be closely following his work in this lecture. So, but before we go, I dive into the problem of Benard-Marangoni convection, let us first recall the jump conditions at an interface, because these are crucial for us to understand how to set up the problem, especially the interface conditions. Now, consider an arbitrary interface. We'll say the fluid below is minus and the fluid above is plus, and on this interface, let's say we define a normal vector, a tangent vector. Now, if we have such a condition, then we can write down the tangential stress sum condition at this interface. We've already seen that this can be written as n dot tau dot T of the fluid above minus of the fluid below. This is minus T hat dot surface gradient of the surface tension. And you may recall that the quantity tau is the deviatoric stress tensor, and it's equal to 2 mu s for a Newtonian fluid, where S is the strain rate tensor. Now let's look at the situations where we could, this additional term on the right hand side, the Marangoni stress, can lead to convection. Now let us consider a flat interface where this is my flat interface, where I basically am able to bring a hot filament to one side of this interface. So if I bring a hot filament, I have on the left side, let's say it's hot, on the right side it's cold. And when you bring a hot filament or you heat up a certain portion of the interface, that the surface tension in that region will be lowered and the surface tension on the other side will increase. The reason this happens is, for most fluids, you can assume that surface tension is given by this relation, gamma is gamma naught times 1 minus delta T minus T naught. So this this relationship allows us to understand how surface tension varies with temperature. You can clearly see that when the temperature is equal to T naught, the surface tension is gamma naught, and this quantity delta is like a sensitivity parameter. It tells us how sensitive is the surface tension of a at an interface to temperature variations. Now delta is positive, therefore when you increase temperature, surface tension decreases. And this model is a fairly good model for a large class of fluids. Now when you create a temperature difference at the interface, which leads to surface tension. Now surface tension, what it does is, we have already seen that fluid would move from regions of lower surface tension to higher surface tension. So in other words, you have a motion in this way. So this is a motion along the interface as well. So let's look at the velocity profile in both the fluids. So it's, let's say in the fluid below, you could have a motion set up like this, and the fluid above you could have motion set up in the following fashion. Now this motion, basically in this case, I'm showing that it's going from regions of higher surface tension to lower surface tension, lower surface tension to higher surface tension, sorry. Now it's important to understand that motion at the interface will lead to motion in the bulk. Now this is one case where we could actually, because of heat from along the interface, now you could actually have a situation where in the experiment, let's say the kind of experiment that Benard had set up, let's assume it to be, let's say, a flat interface. If you assume a flat interface, then what we have now is we have a hot surface at the bottom, and on the top the temperature is fixed at fixed and cold. Now this could just be the atmospheric pressure maintained at a constant temperature, and when you heat up the fluid from the bottom, tiny undulations are possible to the interface, or tiny temperature variations are possible at the interface, and these tiny temperature variations could be because of tiny variations in the heat from the heater below, or it could just be small disturbances from the air above, where the temperature in the air slightly fluctuates, and that could lead to small differences in the temperature. Let us consider a situation where the temperature in the middle in the middle is slightly on the lower side, and the temperature delta T is the fluctuation of the temperature, is slightly higher on both sides. Now immediately what this would do is it would drive a motion because of surface tension variations. Now the surface tension on the sides, because the temperature is slightly higher, the surface tension slightly drops there, but the surface tension in the middle is slightly more. And again, as you know, the fluid would be dragged from regions of lower surface tension to higher surface tension. So at the interface we have a motion in this way, and what would then happen is you have a motion that's basically along the interface, which has to be consistent with motion in the bulk. And this motion in the bulk, so fluid would basically converge to the middle where the temperature is slightly lowered, but then it can't stay there, so it has to go down, and you can end up setting a convection pattern. So we have set up a convection pattern. Of course, I'm showing this in 2 dimensions, but this phenomena really happens in 3 dimensions in an experiment. Now you could also have another situation where you have a container in which there is a fluid. This fluid actually contains mixture of 2 liquids with different surface tensions. Alcohol and alcohol and water is one example. So water and alcohol are miscible in each other, but each of them have a different surface tension. The alcohol-air interface and the water-air interface have different surface tensions. Now if we were to create such a system and expose it to the atmosphere, as we know, alcohol evaporates is more volatile than water, and let us consider a situation where alcohol is evaporating a bit more somewhere in the middle. On the sides, alcohol is, let's say, hardly evaporating, or maybe much less evaporating, okay, or not evaporating at all. Now if this happens, then you would again have a situation where alcohol, you have differences in the concentration of the fluids in the bulk. So we know that alcohol surface tension of alcohol is less than the surface tension of water. So when alcohol evaporates in the middle, then in this region, right in the bulk, you have a water rich region. This water rich region basically causes the local surface tension to be slightly higher, and the other regions the surface tension is slightly lower, because there you have more alcohol compared to the region that I've sketched, okay, compared to the water rich region. So again, now convection would motion at the interface would be set up. This motion at the interface would go from regions of lower surface tension to higher surface tension. So it would have a motion this way, and as a result you would have a bulk motion set up in the following fashion. So again we see that evaporation driven this is an evaporation driven instability. So we have seen 3 examples here. We can have We have seen three possibilities here. I have not showing the the other possibility, which is a surfactant driven instability. You could have same problem exactly like temperature, but now you could have slight differences in surfactant concentration at the interface, and this differences in surfactant concentration leads to differences in surface tension, and that could again generate a similar convection pattern. Now, having studied this, now we will basically looked at this. We'll now look at the Benard-Marangoni instability. The plan for this problem is as follows. We will write down the governing equations in the dimensional form, and then we'll define non-dimensional variables, and then we will derive the non-dimensional equations. And after deriving the non-dimensional equations, we'll look at the base state of the system. Let's start with the problem setup. So what we have is a flat plate at the bottom, and this flat plate at the bottom is held at a temperature of T1. Okay, this temperature T1 could be set up because of using the heating filament at the bottom. Note that a heating filament in general will provide a constant flux condition, but you can always modify the apparatus to generate a isothermal condition as well if you carefully set up the experiment. Now, the analysis can easily be extended to a constant flux problem as well, boundary condition as well, but I'll restrict myself only to a isothermal case. Now you have a liquid here, and the liquid above the liquid is atmosphere at constant temperature T0. So the atmosphere, will treat it to be passive. By passive we mean the viscosity of the atmosphere does not play any role, so we can assume it to be 0. And we will say that the length scale is the characteristic length scale in the problem is the thickness of the liquid in this above this container. We will also assume that the horizontal extent is very, very large, which means that we don't need to worry about end conditions on the right hand side. We will not be employing the lubrication approximation, but it just allows us to basically later on when we set up the linear stability problem, we will be able to assume normal modes of Fourier decomposition in the horizontal direction. Let's write down the Buzynski equations. Okay, so well, one more thing that I have to mention is we have a coordinate system as follows. X is on the surface, X and Y are on the plate, and Z is perpendicular to the plate. X and Y are on the plate, and we also have a gravity term downwards, where this gravity vector maybe I'll write it on this side. The gravity vector G bar would be minus G times Ez, where Ez is the unit vector along Z direction. Now we'll write down the main governing equations. These are Buzynski equations in the dimensional form. So my continuity equation will be just del dot U. My momentum equation in the Buzynski approximation would be, well, let me first write down the general version of it, and then we will tell you what the Buzynski approximation is for students who may not know what this approximation is. If the density is rho, then I have del U by del T plus U dot grad U. Note that I'm putting a tilde because I want to say that these are dimensional variables. this would be something like rho g on the right hand side. Now we have gravity term at P plus mu del square u. This is what we have. Now if you notice this term here, rho g minus grad P, we can further write this as rho minus rho naught plus rho naught into g minus grad P. Okay. We will now say let P be a P. I should not forget that these are all dimensional quantities. So P will be P hydrostatic plus a P dynamic. Then what I have now is this term essentially becomes rho minus rho naught times G plus rho naught times G minus grad pH times PD. Okay, and this essentially gives us rho naught times G minus grad pH. This is the one term, plus I have one more term which is rho minus rho naught of G minus grad PD. Right? So this term can be assumed to be 0 since pH is hydrostatic pressure. I define a hydrostatic pressure such that gradient of this hydrostatic pressure is exactly equal to rho g, rho naught times g, where rho naught is the density of the constant density of the fluid. Right? Now what we then have, have is just rho minus rho naught of G minus grad PD. This is what we have, where PD here is a dynamic pressure. That's the dynamic pressure. Now if we basically substitute this into the equations, then we clearly see that there's a term which is the gravity term here now is rho minus rho naught times G, which tells us that we have a gravity term only becomes important, or buoyancy term becomes important only when the density varies from its mean value or a constant value rho naught. Right? So this can be in the current setup. We can think of the before the start of the experiment, before I start the heater, the temperature of the entire liquid bath is at a constant temperature of T naught, that is at T equal to 0. And then when I start and then you have a hydrostatic pressure in the liquid, there is no motion. Okay, and you do not have PD, you only have pH, that is the hydrostatic pressure, and the density is rho naught. And after you start the heater, when the temperature reaches T1, you could actually have convection, and if there is motion in the bulk, then you have a dynamic pressure pH. Okay. Now in the Boussinesq approximation, what we do is we say that this gravity term, the density variations are only important in the gravity term and in no other term. So one can systematically expand, like for example, in the inertial terms you have density rho. This rho can also be thought of as some mean value rho naught. Let me write that down. So in the inertial term that you have here, you can say that is rho naught plus a delta rho, that is the fluctuation of the density. And what we do is we ignore the fluctuations in density in all terms except the gravity term, and this gives us the Boussinesq approximation. The Boussinesq approximation basically one can systematically analyze the validity of the Boussinesq approximation, the limits of this approximation, but that will be beyond this course. Professor Gary Leal's book on advanced transport phenomena, one of the books recommended for this course, contains a discussion on this topic. So now with the Boussinesq equation, we have a approximation, what we have is the left hand side, you have density becomes rho naught times del u bar by del t plus u dot grad u. This is rho minus rho naught of g minus grad pd plus mu del square u. This is what we have. This is my momentum equation. We also need to couple this with the temperature equation. The temperature equation would be rho naught times Cp naught so here this is specific heat at constant pressure, and K is thermal conductivity. Okay. Now we can define a few simple parameters. Define, let's say, kinematic viscosity nu naught, which is mu by rho naught. That is the kinematic viscosity. And as we know, the kinematic viscosity units would be meter square per second, and the units. And we can also define another parameter, which I'll call it as alpha naught, and this alpha naught would be K by rho naught Cp naught. This is called the thermal diffusivity. Just like kinematic viscosity tells us about the diffusion of momentum, alpha naught tells us the diffusion of temperature, and this units also will be meter square per second. Okay, so now we can immediately define a new parameter called the Prandtl number. Prandtl was Ludwig Prandtl was the creator of boundary layer theory. He's also called the father of modern fluid mechanics, and so the Prandtl number essentially would be nu naught by alpha naught. Okay, so now that we have this, we can proceed with non-dimensionalization. So we first define the non-dimensional variables. The non-dimensional variables would be x bar would be x by d, where x is a vector here, and velocity I will non-dimensionalize as u tilde by uc. This will be the characteristic velocity. We will define the characteristic velocity in a minute, and t will be t tilde by d by uc. Pressure will take it as P by rho u naught uc square, rho naught uc square. And finally we have temperature as well. Now for temperature, what we want to do is we want to define a non-dimensional variable whose value is between 0 and 1. Because temperature, when you heat the fluid at the bottom at T, if you heat the fluid from the bottom, the fluid at the bottom will have temperature T1 and the fluid at the top will be close to temperature T0. Therefore, anywhere in the bulk you could expect the temperature between T1 and T0. So to define a variable whose value is between 0 and 1, we will consider the variation at any point, variation of the temperature between the hot plate at the bottom at any point in the bulk. So that will be T1 minus T tilde, and then we will divide it by the maximum variation that is possible. That's T1 minus T0. Okay. Now, one of the things that I did not mention is that we have density terms in the momentum equation. We have temperature equation. What's the connection between the density and the temperature? So in the density and the temperature will vary like this. The density rho would be rho naught times 1 minus beta T minus T naught. This beta is called the coefficient of thermal expansion. So if the fluid locally expands because of local heating, local increase in temperature, then the local density would decrease. And the rate at which the sensitivity of density field to temperature field is given by this parameter beta. Now you can straight away calculate from this. In the equation, what we have is, we have this term rho minus rho naught times G. This should be rho tilde minus rho naught times G. This rho tilde minus rho naught times G essentially becomes, or just look at the rho tilde minus rho naught. This essentially becomes minus beta of rho naught into T minus T naught. Right? So now I don't have to worry about variations in density anymore. If I know the variations in temperature, that's enough to solve the problem. Okay. So let's write down the equations. If I substitute these non-dimensional variables into my equations, then I get the non-dimensional equations. Let me write that down. The non-dimensional equations would be, the continuity equation remains the same. The momentum equation, we have divided throughout by rho naught density. So what we have is del u bar by del t plus u bar dot grad u will be minus grad p. So p would be p tilde d. Just put a subscript d there. P tilde d plus the viscous term, let me write that down, that will be nu naught by uc times d times del square u, and finally we have the gravity term. Let's look at the gravity term. So what will be the gravity term here? Now what we have in the equations is minus beta rho naught T minus T naught in G. Gravity force or body force. This is the term that we have. Now since I know the expression for theta, now I can write down I can write down theta t1 minus theta t0 will be t1 minus t tilde, and what we are interested in is t tilde minus t naught. So t tilde minus t naught in terms of theta essentially becomes t1 minus t0 of 1 minus theta. Okay. So therefore my gravity term essentially becomes minus beta rho naught of t1 minus t0. This is a vector g, that is 1 minus theta times the vector g, and this essentially becomes minus beta rho naught t1 minus t0 1 minus theta. This gravity becomes minus g Ez. So what enters our equations, this is a side notes, what enters our equations now is plus beta t1 minus t naught into g d by uc square of 1 minus theta into Ez. Note that I have divided throughout by uc square by d. That's why there is the coefficient of the inertial terms on the left hand side is 1. And finally we have an equation for temperature, but now the temperature variable is theta. So we have del theta by del T plus u dot grad theta, where u is a vector here. This becomes 1 by Prandtl number times nu naught by uc times d del square of theta. These are my non-dimensional equations. Okay. Now, if you notice here, there are two terms that I am highlighting. These two terms are nu naught by uc times d. So we can say that this, because this is not a shear driven problem, there is no natural characteristic velocity field that is coming externally. Any velocity field that is generated is because of either buoyancy or because of surface tension variations. So this term here is actually the Reynolds number. uc into d by nu is the Reynolds number. But since it is not a Reynolds number, we don't expect Reynolds number to be a very important parameter. We can set uc to be nu naught by d, meaning this uc now becomes the diffusion velocity. And it immediately tells us that the characteristic time scale let's call it as Tref, okay, or a reference time scale. This becomes d by uc. This is nothing but d square by nu naught. This is the diffusion time scale. So that's what we have. And finally we have one more interesting parameter, which is if we substitute the expression for uc into the term that I'm highlighting, this term in green, the green box, this term basically becomes another non-dimensional number. It's called the Grashof number, that is gr, and this Grashof number is beta t1 minus t0 into g. We have a d there, but now we also have uc at the denominator. If I substitute the expression for uc, I am going to get nu naught square times d cube. This number tells us the ratio between buoyancy force to viscous force. Okay, so let's write down the non-dimensional equations in a more compact form. The non-dimensional equations would be del dot u is 0, del u by del t plus u dot grad u will be minus grad p plus del square u plus Grashof times 1 minus theta times Ez, and the other equation, the temperature equation, becomes del theta by del t plus u dot grad theta is 1 by Prandtl number times del square of theta. So we basically have two non-dimensional numbers that enter the discussion, the Grashof number and the Prandtl number. So I think this is a good time to stop. What we have done in today's lecture is to start with the governing equations for the Boussinesq approximation with the governing equations for a heated fluid from below. We've written down the equations in non-dimensional form. Then we have derived defined some new parameters, primarily the thermal diffusivity alpha naught and the non-dimensional number Prandtl number, which is a ratio of kinematic to thermal diffusivity, kinematic viscosity to thermal diffusivity. And then we have non-dimensional variables have been defined. We've assumed the linear variation for density with temperature, and we then derive the non-dimensional form of these equations. Now what we will do next is to derive the base state. We have to define the boundary conditions systematically for these problems, and then the plan is to perturb the flow and the temperature field above that base state to derive linearized equations, which will take it up in the next lecture. Thank you.